This is the Calculus AB 3.6 review. Calculators are allowed, and this is number 9. So on all three of these, we are looking to find the derivative of the inverse function for each of the given functions. Now the problem with these three is that if we were to use our pre-calculus techniques to try and find the inverse explicitly, it wouldn't work because I would replace this with an x, these two with y's, and I would try to isolate the y. And in none of these scenarios would I be able to isolate the y. So what that means is we have to use the relationship that we know between derivatives of originals and derivatives of inverses. So what I would suggest on each of these is that you set up a chart, because on both you're going to have a function and you're going to have the function's inverse. On the function you will have a point, and on the inverse you will have a point. And on the original you will have a derivative, and on the inverse you will have a derivative. Now what's critical to remember is that we are told x is 2 on the inverse function. So that means we know the x coordinate on the inverse. If you remember your relationships between inverses and originals, the x's and y's switch. So that means if the x coordinate on the inverse is a 2, then the y coordinate on the original will be a 2. So in order to find that x coordinate, we need to solve for when the function equals that output, and we'll solve it with respect to x. So you can either see that the answer is 1, or you can put that into your calculator and solve it and find that the x coordinate will be 1. Because the x coordinate on the original is 1, that means the y coordinate on the inverse will be 1. Now this x coordinate on the original function is what's going to go into the derivative of the original. So if I take the derivative of this original function, I will get a 5x to the 4th plus a 1. And if I plug 1 in, then I will get a 5 times a 1 to the 4th plus a 1 will give me a 6. Now the inverse's derivative at its x coordinate is the reciprocal of this point, because what's happening is we're changing a dy dx into a dx dy. We are shifting the x and y's. That's how inverses work. We trade all the x's and y's. So when we trade the x and y on this slope, we end up getting a dx dy. So the coordinating points, the corresponding points, are going to have slopes that are reciprocals of each other. So that one was part A. If we look at part B, again we're going to need that derivative, so I'll go ahead and take it while we're up here. And I will set up my chart, because sometimes organizing it in the chart is actually more helpful. We were given the x coordinate of the inverse is 13. The y coordinate we don't know, but we do know the y coordinate on the original has to be 13. So I can solve for when this original function equals 13, and I can do it on my calculator and end up getting x equals, I don't know, so I'm actually going to pull this one out. It's probably 2. That'd be 8 plus a 4. Yeah, x equals 2. So you could find that on your calculator if you needed to, but I think for the most part they're going to come out as nice whole even small numbers. So we've got this point on f, which means we can now get the slope that goes with f. That means I'll plug that 2 into the derivative of the original function. 2 squared is 4 times 3 is 12, plus 2 gives me 14. So that derivative at 2 on the original function was 14. That means the derivative of the inverse at its x coordinate that corresponds to the original point will be the reciprocal of the 14. Last but not least, we'll do part C, which works the same way. We've got our function, We're going to need its derivative. And we'll set up our chart for the function and for its inverse. We know there's a point for both. We know there's a slope for both. The point information that we were given is that the inverse has an x-coordinate of 1. That means the original will have a y-coordinate of 1. So I will be solving for when the original function equals 1. Well, that happens when x is 0. So that means I need the slope of the original one computed at that point. Plug 0 into this, I get a 0 plus a 5 minus nothing. So that gives me a 5. So the inverse's derivative at its associated point will be the reciprocal of that 5.